Hello and welcome back. In this video, we're going to take a look at how we work with matrices in order to simplify a system. So specifically, we'll focus on the key strategies of how this method of Gaussian elimination works. So it's very important that we set these problems up in a specific way, because once we do, our elementary row operations take effect and the algorithm takes place almost identically each time. So before we proceed with this example, which we have looked at in the form of elimination, let's define a 2x2 linear system. So 2x2 just means there are two equations and two variables. Now you can still have two variables and you can have three equations, but if you think about what that means, that would mean that you have three lines and you're looking for where all three of them intersect. How likely is that three lines all intersect in exactly the same spot? So in this 2x2 case, let's say that we have ax plus by, and here we have cx plus dy. And for the sake of argument, let's just say these equal some constants f and g. So a, b, c, d, f, and g are all constants. X and y are the two variables that we're working with. In matrix form, this would be represented as a, b, f for the first row, and c, d, g for the second row. The optional bar here is just to denote that that's where the equal sign is located. So once again, just notice that our x and y columns appear as the two variable columns from left to right. You could have the y variables listed first and then x. It doesn't have to be in alphabetical order. It's just intuitive that way. And then here we have our constants. So it's important that our matrices are set up this way each and every time because of the way we execute this algorithm. So what we want in the end is we want something that looks like this: 1, 0, something, and 0, 1, something else. And I'm just denoting those with question mark and double question mark. And the reason we want that is because when we read this matrix off as our final solution, keep in mind that this is still equivalent to the original system that we dealt with. So this would read 1x plus 0y equals question mark, that whatever that constant value is. And the second equation would be 0x plus 1y equals something else, which really just means that x and y are equal to those two constants. So we can see that the format that we want is this 1, 0, 0, 1 for this 2x2 system. Let's go ahead and execute that task now. So in this first system, we know that there are three row operations that we can perform. There's switching two rows or interchanging two rows. We can also choose to scale a row by a constant or add a multiple of a row to another row. So I'm going to begin by just converting this to matrix form and say this is 4, 3, 9, 2, 6, 10. We've got to be careful when we read these off. We see that the x coefficients are 4 and 2, therefore that's going to be our first column. Our y coefficients are 3 and 6, that's our second column. And then equals, 9, 10, those are our constants, which is our third column. So the first thing that I'm going to do here is, because my first task is going to be to eliminate the leftmost coefficient in the second row, I want this the second equation to eliminate the x. And so I don't want to work with fractions personally. I mean, you can take -1/2 of row 1 and add it to row 2, but I'm going to choose to swap row 1 and row 2. So the way I'm going to write that is I'm going to swap row 1 and row 2. So I'm going to interchange them. And so all that's going to give me is 2, 6, 10, 4, 3, 9. And intuitively, all we've done here is we've just interchanged the two equations. They still intersect at the same point. The next thing that I'm going to choose to do is I'm going to take, I see that if I take -2 times 2 and add it to 4, I'm going to get 0. So the second operation that I'm going to do is just to eliminate the x coefficient in the second equation. -2 times row 1 added to row 2, and input that result into row 2. So I can use, if I want, I can just say I'm going to take -2 times this first row, and I'm going to add it to the second row. That means we're not changing the first row. We're we're using it to help us cancel out the second components in the second row. So I'll have 2, 6, 10. Negative 2 times 2 plus 4 is 0. Negative 2 times 6 is negative 12, plus 3 is negative 9. Negative 2 times 10 is negative 20. Added to 9 is 11. Awesome. So now I'm getting closer to this 1, 0 structure. You can see that I have a 0 in the lower left portion already. So my next task is, well, I think what I would like to see here is I want to obtain this 1 coefficient here. This is not necessarily the operation that you have to do, but it's the operation that I'm going to choose to do. So I am going to take 1/2 of row 1. And that's going to be the new row 1. Okay, so 1/2 of row 1, 1/2 of all of these values. I have 1/2 of 2 is 1, 1/2 of 6 is 3, 1/2 of 10 is 5. And then my second row is unchanged, 0, negative 9, 11. So far what we've achieved is that we have the 1, 0. So we have the first column where we need it. Now we're going to move inward into the second column. And the first thing that I'm going to do is I am going to convert this negative 9 into a 1. So it's kind of like we work our way, if you think about it, we work our way down. So we make this a 1. Then we make this, rather backwards. We make, step 1 is to make this a 0. And then once we have the 0 here, we'll make this into a 1. Then we'll make this into a 1. And we'll use that second row to make this a 0. Okay, so we have executed the first step, the second step, which is to get a 0 here. We've done that. We have a 1 here. Next, I'm going to move to the second row, work my way inward. So I'm going to make this negative 9 into a 1, and then I'm going to use that to help me make this 3 into a 0. Okay, so to make that negative 9 into a 1, well, the only way I could really do it is to take negative 1/9, or divide row 2 by 9, and store that result into row 2. So I'm going to leave the first row unchanged, 1, 3, 5. Second row will become 0, 1, because negative 1/9 times negative 9. And then I'm going to take negative 1/9 times 11, which is, I'm sorry, this should be negative 11 here. It should be negative 11 because negative 2 times 10 is negative 20, added to 9 is negative 11. So that is going to be 11/9. All right, so far I have a 0 here. I have a 1 here. I now have a 1 here. Now I'm going to finally use that to algorithmically eliminate the 3 that I have here. So how am I going to do that? Well, if I take negative 3 times row 2, I add it to row 1, and I store that result in row 1, I'll be in good shape. Okay, so negative 3 times the second row added to the first row. So the second row is unchanged, 0, 1, 11/9. Negative 3 times 0 added to 1 is 1. And now you can see why we get this 0 here first before we use the second row to help us cancel out the y coefficient. If this were not a 0 and we added some multiple of a non-zero value to 1, we would change that 1 back to something else and we'd kind of be going around in circles. Negative 3 times 1 added to 3 is 0. Negative 3 times 11/9 added to 5. Well, I can do that in my calculator. Negative 3 times 11/9 added to 5. Convert that to a fraction. That's going to give us 4/3. And we're effectively done. We now have the original form we were hunting for, which was the 1, 0, 0, 1 structure. And that means that now we can read off the equations again, keeping in mind this is still equivalent to our original system, where this first equation reads 1x plus 0y equals 4/3, or x equals 4/3. And the second equation reads 0x plus 1y equals 11/9, or y equals 11/9. And now we can state our solution as an ordered pair or as a vector, and we are all set to go. We have solved that system.